Uh, the voltage and the current can be directly measured.
Yes, the voltage and the current can be directly measured. And what information must be estimated?
SOC, SOH,
Yes,
cycle
exactly.
time.
Yes, exactly. The state of the charge and state of health. We can directly measure the voltage and the current of our battery pack and some estimation like SOC and SOH. Okay. And now these slides give us like complete direction of this presentation. As you can see on this the left side, we have this real battery pack on the right, real battery pack, and you can see on the right we have its virtual twin, and between them data is continuously exchanged, and the system like senses the here the system is sensing, doing some analysis and prediction and optimize, and at the end it finally protects over the battery pack. And here the reactive protection means, as you can see that the reactive protection means the BMS waits for a limit to be reached. For example, like if a cell voltage becomes too high and the BMS opens the contractor. I hope you know the contractor. There are contractors like this. If you will see that diagram of the contactor. So there the contactor or reduces the charging dead time. So that is like a predictive. If we if I talk about the predictive intelligence, it is bit different, and it just studies the trends and tries to identify that the cell is moving towards an unsafe condition before the limit is crossed. So this gives the controller more time to react smoothly. And the lower part of this slide you can see here. Just give me a second. Uh, yeah, as we can see, the main capabilities is the real-time battery monitoring. Okay, and here the AI-based state estimation and some virtual battery simulation we can do also here, and some predictive safety and maintenance and the intelligent charging and life cycle at the end. So these capabilities are connected together, and for the better monitoring, for the better data, or after getting this better data, we can improve the estimation, and the better estimation will help us to lead to the safer control. Okay, but please remember one thing, that the AI doesn't replace basic BMS protection. Okay, so the hard safety limits, I will say, like the contactor and the protection logic must still exist there. So AI is an like intelligence, additional intelligence layer that helps the system make earlier and more adaptive decision. Okay, and here the one one question arises here, like why smarter BMS is essential. Okay, and if I talk about from the market scenario, like this, the we know that the EV industry is growing rapidly, and like every vehicle generates a large amount of battery data. So basically, this slide is just like highlighting that more than 20 plus million of electric cars sold in 2025, and around 1.2 terawatt terawatt hour of electric battery deployment. So whether we focus on the exact market number or like the overall trend, so though the main important message is that the battery scale and the data complexity are increasing very quickly here. So a battery pack contains we know that a battery pack contains many cells, and each cell may behave slightly different because of the manufacturing variations and some temperature difference or like aging and load distribution. Okay, so vehicles are operating in different climates and like different condition. So if fixed rules set cannot always provide us the best result. So a small improvement becomes very valuable at the large scale. For example, a small increase in battery life can reduce the replacement cost and material demand, right? So a small improvement, if we say in the charging efficiency, can save us a large amount of energy across a fleet. So before fault prediction, which can prevent the breakdowns and like improve the customer confidence, and better thermal safety, which can reduce the chance of serious incidents. So a smarter BMS is like not only about adding advanced software. So it is like directly affects the battery lifetime and charging efficiency, failure prediction, thermal safety, and fleet availability. So these are like some technical benefits, benefits of this, but they like also become economic and environment benefits of this smarter BMS. Okay. Now let's some understand about the limitations of conventional BMS versus smart BMS. Okay. As we know that a conventional BMS performs like essential tasks very well, like like it measures the voltage, current, and temperature, checks fixed threshold, and activates the protection. So the problem is that it is mainly rule based and reactive. For example, the system may have a rule that charging must stop when a cell reaches a maximum voltage, right? And that rule is necessary, but it does not explain why one cell is reaching the limit earlier than the others. So it also doesn't predict whether the same cell will become a repeated problem after another 50 cells. So it is just, this slide is just showing that the some list common limitations or the dependence on fixed thresholds, like limited adaptation to aging and environmental changes, which reduce the accuracy when the battery becomes old. So difficulty in detecting in gradual faults as well. Okay, so limited use of historical data is not enough there. So a conventional BMS may detect an abnormal condition and trigger a warning and reduce power or isolate the battery. But a smart BMS tries to go further and detect early deviation or identify the likely cause, or the predict progression, or optimize the operation and prevent the failure. Okay. So a useful example I will say is fever detection. A fever detection means a thermometer can tell us that the body temperature is already high, right? So a more intelligent medical system also looks at the trend, like symptoms and history, to understand the cause and the future risk. Okay, so smart battery management system follows this similar idea. Okay, the main thing is that it do not criticize the conventional protection, but it just explain its remain necessary, but it is not sufficient for the predictive operation. Okay. So, before adding intelligence, we should be clear about the basic function every BMS must perform. Okay. So, basically, this here you can see that I hope everyone can easily read this because the text size is little bit smaller here. I hope everyone can easily read this. Okay. So, this basically slide shows the BMS as the central controller of the battery pack, and it receives signals from battery cells, current sensors, temperature sensors, insulation monitoring, and interlocking circuits, right? So if it then controls the contactors or cooling, charging, or communication with the vehicle control unit, and some you can see the cloud platform as well. Okay, so the first function is measurement, and the BMS reads cell voltage, pack voltage, current, and temperature. We all know that. So the second function is the state estimation, and it estimates states of charge, state of health, state of power, and sometimes remaining useful life as well. So these values cannot all be measured directly. So the and then if I will talk about the third function is the protection. And the BMS protect against the over voltage, under voltage, over current, short circuit, or some excessive temperature, insulation faults, right? Then if I will say like the fourth or the main function, I would say is the control, right? Like it manages the contactors or do the cell balancing, charge and discharge limits, and also do like the thermal management request as well, right? So the main or the a good way to explain this is to call the BMS the battery nervous system, and the sensors are like the sense organs, and the controller is the brain of our EV. Okay, and the contactors or the cooling devices are the actuators here, and the CAN communication connects the battery with the rest of the vehicle. Okay, so just these are the just the main core function of our battery management system. If anyone don't have that much knowledge about the BMS, that's why I just explained here. But the main topic is our to understand about the digital twin, right? So now we have understood that what additional capabilities make this BMS truly smart here. Okay, so let's see here. So a smart BMS combines the conventional protection with adaptive modeling, right? And like AI analytics and connected service. So the key difference is not only like more sensors, so but it is like the ability to learn from the data and the data and to improve the decisions. So as you can see here from the left side, the smart BMS capabilities here, you can see that the system learns battery behavior from historical and the real time data. So it continuously corrects model parameters. It what it do? It continuously corrects model parameters and estimates the internal states that cannot be measured directly, or detects the weak cells um, and abnormal patterns as well, and predicts the future capacity and the resistance, and selects the charging and the cooling actions. Then it detects the weak cells, or like it provides the confidence and the uncertainty values with its prediction as well. Okay, and here is the staircase on the right, which shows us the five intelligence level. Level one is the monitoring, like what is happening. Then the level two is the diagnosis. Here, what is why is it happening? Then level three is the prediction, what is likely to happen next. Okay, then we have level four is the prescription, like what action should be taken. Then the level five is the autonomous optimization. Autonomous optimization is uh, like can the system safely adjust itself within the approved limits. So the progression is important. Like many systems are called the smart simply because they are like they display more data, right? And true intelligence begins when the system interprets the data and predicts the future behavior and supports better control decisions. However, autonomous action must always remain inside verified safety boundaries, I will say. Okay, so you can use these five steps staircase as the main to know about the intelligence levels of our BMS. Okay, then the main technology that supports this intelligence is the battery digital twin. Then what exactly this battery digital twin is? So a battery digital twin is a continuously updated digital representation of a physical cell, okay, or the module or the full battery pack. Okay, so it is not just a 3D drawing. It must like represent the battery's charging state, conditions, and like the behavior over time. Okay, so the digital twin here combines the physical measurements or mathematical battery models, some historical operating data, or like environmental conditions, and some AI algorithms. Okay, so like most importantly, it has a two-way communication with the physical system. Just give me a second. Okay, so where I was, yeah. So it also it has two-way communication with the physical system, and here the battery send measurements to the twin, and the twin send the prediction, or it just update the parameters or recommend the action back to the BMS. Okay, so here this circular diagram shows the operating cycles. First we sense the battery. Okay, first what we do, first we sense the physical battery, second we synchronize it, we synchronize the virtual model with this the current data. Okay, then the third we can what we can do is like we simulate the pause this we simulate this multi-physics, or what I would say the data we are getting from the simulation part. Then the fourth, we can predict the state, behavior, and the future parameters. Okay, and at the end, fifth, we have or we optimize the decision and the control action. Then this cycle is continuously repeating again and again like this. For example, the twin may receive current voltage, temperature from the back. So it updates its model and estimates its internal resistance. I hope everyone is getting what I am trying to say. Okay. So this for giving this example, I hope you will understand this. Like, sorry, is anyone saying anything? Okay. So the twin may receive like the current voltage and temperature from the pack. So it just updates its model and estimates the internal resistance. Okay. And it then simulates whether the present charging current will cause the excessive heating, and suppose if the risk is predicted, so it will just recommend a lower current or the more cooling that time. So this continuously closed loop is what makes the twin useful here. Okay, so this is basically or exactly what battery digital twin is. It just first it what it does the sense, then it synchronize the data or with the help of two-way communication, then it simulate with the virtual model or the 3D model, then it just predict the state or behavior or the future performance of the battery pack, and at the end it just optimize or take the decision whether it has to increase or the life of the cells. Okay, so it just at the end of. Okay, now let's see how all the physical embedded edges, cloud and application layers connect together. Okay, so basically this here you can see that it is the complete system architecture in 5 layers: layer 1, layer 2, layer 3, layer 4, and then this is the layer 5. Okay, let's start from the bottom here. First we can see here the layer 1, which is the physical battery layer. Okay, because here the intelligence depends on the strong physical foundation. Okay, and layer 1 is the physical battery layer. Here we can see that the cells and modules are here: bush bars, contactors, cooling equipments, then we have the voltage and temperature sensors and insulation monitoring, right? And layer 2 is the embedded BMS layer here, and here you can see it performs the signal acquisition, uh, or like the filtering or just filter or protection logic, some SOC and protect, or this power estimation. Then the here we also have the CAN communication or the vehicle communication. Then in the third layer we have is the edge intelligence layer. So this is where like fast local analytics can run, such as feature extraction, anomaly detection, lightweight AI models, and local digital twin corrections. Right, and then we have here one more thing is that about this intelligence layer is because the edge processing is valuable because it can respond immediately without waiting for the cloud. Okay, then in the layer fourth we have a cloud or a fleet layer. So it supports long-term storage, model training, degradation analytics, predictive maintenance, fleet benchmarking, and large digital twin simulation. Okay. Then at the end we have the last layer five, the application layer. Um, I hope you have joined the last time I have given the webinar on CAN system. There I had shown you the 7-layer OSI model, open system interconnection model. There I have taught you about the physical layer or the data link layer in which CAN works. Is anyone does anyone have attended that webinar of CAN communication? You can open your mic as well, okay? Because I can't able to see the chat box right now. Okay, so then the last five layer is the application layer. Okay, where the information is used for the range prediction, service diagnosis, charging optimization, and we have the warranty analysis and second life assessment. So, and you can see here the arrows. What arrows is exactly showing here? The arrow shows two directions, and the data moves upward from the physical battery to higher level analytics, or like updated models, threshold policies, and control recommendation moves downward. Here is the upward direction of the like it's just showing the physical battery to high level analytics, then updated models threshold, or some policies or control recommendation which are moving towards downward here. Basically this like layer designed uh, just because to help the separate safety critical local control from the computation. Okay, and some heavy fleet learning. Okay, so the main thing is like every layer depends on the data, so that we can examine what exactly the digital twin requires. Okay, so we need in this a 5 layer: first the physical battery layer, then the embedded BMS layer, then edge intelligence layer, then the cloud, then the application layer. Okay, application layer is there where we can see with the in our screen as well. Okay, so if I will say the accuracy of the digital twin depends on the quality, relevance, and like synchronization of this data. So the slide separates the data into directly measured and derived information, as you can see here. Like directly measured data includes cells and pack voltage, charge, discharge current, cell or module temperature, charging power. Okay, all these things are included in this. Depth of discharge, time at high SOC, all these things. And the data pipeline is also important here because the ray signals or the raw signals are first validated, then it filtered. First what it does, it do the first it check the validation, then it filters, then convert into useful features, and finally supply to the digital twin. As you can see, you can easily see the digital 3D model of your data, 3D model of your battery pack on your screen, where you can easily identify the, if suppose this cell is got overheated, or this cell got little discharged. So you can easily identify that this cell is only that this cell has the issue of charging or discharging or BMS. So smart BMS just tells you by indicating by the any color, like red color will show here. So you can easily identify or you can easily identify with the help of smart BMS, or uh, or you are continuously watching your this 3D battery pack model in the digital twin technology. And one example I will give you, as you when like doctors also use this technology, they use some cameras to do the for the operation, but the same exact thing we can easily see on your on our monitors as well. So this is the real time data, which is which in which we can easily detect or show the motion of the organs in the live real time. Okay, so that is the same thing which is applying here, the digital twin. You can easily or continuously watching the each cell voltage measuring, which this BMS is measuring. Okay, so this is the basically this what exactly this digital twin is showing us here. Okay, so uh, a very advanced AI model like cannot compensate for poor quality input, or like if I would say in the simple terms, this bad data in which like in will produce unreliable prediction out, or good battery intelligence starts with indisciplined sensing and the data management. Hello. Anyone have any questions till now?
Sir, how to implement this digital twin? Does it require any simulation or we have to use the cloud models?
Just give me a second.
Let's say now we are ready with the sensor data, collected data from different sensors for the physical
Your
battery.
voice is little lower. Can you just speak a bit louder?
1 second, let me.
Hello.
Is it audible
Hello,
now?
hello. Yes, you're
Hello,
audible.
can you hear me now?
Yes, you are.
Yeah. See,
You are.
suppose, now I don't have any physical battery with me. I wanted to implement and see all these concepts what you explained now. So what is the process like? Even I don't have any cloud also. So I just want to use some edge control device, maybe the NVIDIA or maybe the some of the embedded devices. So how to proceed to implement a small prototype
Yes,
for
by the
the
end of
simulation?
this webinar, you will get understanding like how you can implement this, or how you can see the digital twin in a real time. Okay, just give me a few minutes more, then you will get better understanding as well, like how you can implement this technology as well, and how you can see this continuous monitoring system. Okay, and at the
Okay.
end, we will also discuss this. Okay.
Okay, fine.
Yeah. What's your name?
My name is Venkat.
Venkat. Where are you from?
I'm from Bangalore.
Okay, Venkat. Just give me a few minutes, then we will discuss this as well. Okay.
Okay, sure. Thank you.
Yeah. So this is once this reliable data is available, the digital twin uses here the different kinds of battery models as well. Now, if you will observe this picture as well, picture or the slide here, here you can see that no single battery model is ideal, and we also know that no single battery model is ideal for every application, right? a practical digital twin like often combines the several approaches here. Okay, so the first is the electrical model here. Okay, first we have the electrical model, which is commonly an equivalent circuit model. It just uses the resistors, capacitors, and voltage sources to represent the terminal behavior. Okay, and it is relatively simple and suitable for the embedded estimation and the real-time control. And the second is the electrochemical model, which just represents us the lithium transport reaction, kinetics, and the electrode behavior. Okay, so it represents like process such as ion transport and electrode reaction in more physical detail, and it can provide the deeper insight, but normally needs more computation and accurate parameters. Then the third, we have the thermal model. So it predicts cell core and surface temperature and estimates the heat generation and the support cooling system control. And then at the end, we have the fourth, who is the aging thing. And here you can see that this it just estimates the capacity fade and resistance growth using factors such as cycle aging, calendar aging, or SOC temperature and the charging rate. Okay, so the AI or the data driven layer just learns the relationship directly from the battery data, and it can recognize the complex patterns and correct model errors, but it requires representative and carefully labeled data. And if I will say that the strongest digital twin is often hybrid, like physics gives structure and consistency, while the AI captures complex behaviors that the simplified model misses. Okay, so think of it as using several maps of the same city. Like one map shows the road, another shows the traffic, and another shows the weather. So together they support a better decision. Okay, so these models tells us or it shows us the combined multiple approaches, and we know that this thing is all the things which comes together, which helps us to get the real-time data monitoring of our battery pack. So these model like must remain synchronized with the real battery as it changes or ages. Okay, and here you can see that the like synchronizing the battery, physical battery and the virtual twin. Okay, so a digital twin must be regularly corrected so that it continuously to represent the real battery without synchronization, and it slowly becomes a model of an earlier battery condition. Basically, this process begins by reading live voltage, current, and temperature. So the system compares these physical measurements with the model output, and it calculates the residual, which is simply the difference between the measured and the predicted values. Okay, so if the difference is like significant and the consistent, so that time the twin identifies which model parameters may have changed, such as internal resistance, available capacity, or the thermal behavior. So the model is then updated and validate, and after the validation, the correct twin is used for the future prediction and control the graph on this. As you can see here, the slide shows how the predicted this voltage may initially deviate from the physical measurement. So after a parameter update, the prediction move closer to the real curve and the error become smaller. Okay, and some common synchronization method includes the Kalman filter, because and the particle filters as well. Okay, and some recursive least squares. So the key idea is like that synchronization is repeated correction process. Okay, and digital twin that is not synchronized is not like truly a twin. It is just only a historical model here. Now let's look at the AI methods that can support estimation, prediction, and the control. Okay, so these are the basic method. Now I hope we all know that the main basic thing, the SOC, SOH. Okay, so the main thing is that the different battery management task requires different AI methods. Okay, and we should not select an algorithm simply because it is popular. So we should select it accordingly to the task, data volume, required accuracy, explainability, and the hardware limits. Okay, so if I will talk about the traditional machine learning methods such as like linear regression, or this support vector machine, random forest, all those things, they are often easier to train and interpret. And if I will say that deep learning methods such as artificial neural networks, LSTM, GRU, and like transfer, these are the transformer models which are suitable for complex time series patterns. Okay, and degradation, forecasting, and like anomaly detection. So they can learn non-linear behavior, but they normally require more data and computation, right? Like auto encoders can be used to learn normal behavior and detect unusual patterns. Okay, so this thing comes inside the deep learning plus traditional ML. And then if I will say like the enforcement learning, sorry for that, this and reinforcement learning, this can optimize the charging, cooling, or the energy method actions through the rewards and the penalties. However, it like needs strict safety constraints before the physical deployment. And here the physics, or I will say the physics informed AI combines equation with the machine learning. This can reduce like data demand and improve the physical consistency. Okay, so the model selection map on this slide, like just the thing is that it just connects SOC and SOH estimation, RUL, this prediction, fault detection, charging optimization, and like physics consistent modeling with the suitable algorithm families. Okay, so the central lesson is battery task first, model family second. Okay, so now we will now apply these ideas on the most important BMS estimates, which is state of charge. Okay, so here the SOC represents the remaining charge uh, relative to the unusable battery capacity. Okay, so we often compare it with the fuel gauge, but battery SOC is more difficult because it can be measured directly. Because voltage alone is not enough. Battery voltage changes with the SOC, temperature, current, chemistry, and aging. So during operation, current integration can accumulate error because of sensor bias, or like some batteries also have a relative flat voltage region where a small voltage change may correspond to a significant SOC change. Okay, so this slide just shows here a hybrid estimator. First, the current is integration, then we have the model prediction, then the AI correction, then fourth we have the accurate SOC. Okay, so first the current integration tracks charge entering and leaving the batteries. Then second, a battery model predicts the voltage response. Then the third we have the AI correction layers, which learns the remaining error between the model and the real battery. Finally, the online parameter, which keeps updating us the estimator because the estimator aligned on this the battery aging. Okay, so the result is not only a SOC number, but a good estimator should also provide confidence or detect possible sensor bias and indicate the range available to the vehicle controller. Okay, so the graph here is just showing the benefit of the parameter correction. Here you can see the before parameter update large error, then we have the after parameter update narrow error band. So here the detect possible sensor bias, and because it indicates the range available to the vehicle controller. The graph is just showing the benefit of parameter correction before updating, and the error band is wider. After updating, the estimation follows the actual SOC more closely. And this hybrid estimation is powerful because it combines the physical understanding with data-driven tech correction rather than depending on only on one method. Okay, so the SOC like just tells us how much charge is available now. The next concept here is just telling us how healthy the battery has become. Okay, so state of health here describes the like present battery condition compare with its original condition. So in new battery is treated as approximately 100%, as you can see here. As the battery ages, usable capacity decreases and the internal resistance usually increases. So here you can see that the end of the service example is like 80% of SOH is shown here. Okay, so the like there are two common ways of expressing this SOH, like capacity based SOH and resistance based SOH. Okay, so capacity based SOH compares present full charge capacity with the rated initial capacity, and the resistance based SOH compares the present resistance with the internal resistance. And in real application, engineers many engineers may combine several indicators rather than uh, relying on only one number. So here the battery examples shows us the main things, just the progression from new to aged and then towards an end of this service. Okay, so just give me a second, I will drink some water. Just give me a second. Okay. So yeah, so basically this just showing us the new to aged and towards to the end of this service condition. So an aged battery may still operate, but it stores less energy and produces more heat under load and delivers less peak power. So the graph is just showing us the capacity reducing with cycle count and resistance increasing with this this the sorry with this the cycle count. So here the AI can estimate SOH under voltage curve shape. Okay, then it also tells us the temperature response, charging time, relaxation behavior, differential voltage features. So the digital twin advantage is that the system can reconstruct long-term degradation behavior even when the vehicle does not perform a complete laboratory capacity test. Okay, because because we whenever the battery pack comes into the market, there is some testing behind the battery pack. So this degradation behavior, even when the vehicle does not perform a complete laboratory capacity test, SOH is like still more important for the range, because we can easily identify with the help of digital twin. And for the here the for the fast charging limits, warranty decision, or second life assessment, we must you then there we use the AI or the smart enabled BMS. So once we know the present, first we will understand the present BMS. Okay, then uh, then here you can see that the useful life predictions. Okay, so yeah, sorry, just give me a second. Okay, so yeah. Then here is the remaining useful life prediction. Okay, RUL. Basically, it's just showing the estimated operating time, distance, or number of cycles before the battery reaches a defined performance or the safety limits. Okay, so like once we know the present health, we can just try to predict how much useful this life remains. Okay, so this is just RUL is the remaining useful life. Is an estimate of how long the battery can continue before reaching a defined performance or the safety limits. Okay, so the output may be remaining cycles, months, kilometers, energy through output, or the probability of reaching a warranty stage. Okay, so the prediction process begins with here with the present SOC, SOH, and the operating data. Okay, and here this graph is just showing you showing us a capacity trajectory with the prediction band, and here the central line you can see here is the expected future capability. Okay, then like if I if I would say a recommended output format or a predictive value plus a confidence interval or the probability of reaching a target. Like for example, like saying approximately 420 cycles. Okay, with a range is more responsible than claiming the battery will fall exactly on cycle 420. So RUL prediction, this remaining useful life prediction, supports maintenance planning, warranty management, or this what we say release valve or the like some second life decisions as well. Because after a certain period of time, then you might have a need of to change the battery pack. So that time you will get better and idea. You can easily identify the all those things which is or the information from the from the AI enabled BMS. So apart from the energy and the lifetime, a vehicle also needs to know how much power the battery can safely deliver at each movement. Okay, so this the state of power or the SOP represents the battery short duration charge or discharge capability. Okay, so then like this state of power is like constrained by the like maximum and the minimum cell voltages, pack current, all these things, SOC, SOH, internal resistance, all those things comes inside this. So here the BM the gauge or basically this gauge on this slide showing us that just actually my marker this pen is lagging. I don't know why. That's why it's okay. So basically it is basically this the BMS must keep operating inside the approved area. As you can see here, the available power, temporary limit, and the prohibited zone. So the main thing is the vehicle application also here. Then here is the this diagram shows that the power limit is the interaction of like several constraints. A voltage limit may reduce discharge power at lower SOC, right? Or like a current limit may restrict acceleration or charging. Okay, then if I will say the state of power, this state of power affects the acceleration or regenerative braking, fast charging acceptance, all these things. Okay, so a smart BMS just updates these limits dynamically rather than using one fixed value for every condition. Okay, and here you can see that the dynamic limit becomes specifically important when the system detects abnormal thermal behavior. Okay, so the battery faults often develop gradually across multiple signals before any signal threshold is violated. So this is where the AI-based anomaly detection can provide early warnings. And here you can see the early indicators. So normal operation, then we can see here the early deviation, then the increasing risk also here. So this basically these early indicators such as like unusual self-heating or like increasing temperature difference between cells, abnormal voltages. So like any one can indicator may be harmless that time, but a combination and like a trend can reveal a developing fault. So if I would say the normal temperature graph, you will say here, this is the normal behavior of the cell 1, cell 2, cell 3. So in the normal, like this abnormal, or if you will see this abnormal behavior of the graph, so one cell begins to heat faster than the others. So the heat map just this heat map example make this easier to see across a full path. Okay, a normal pack can has a relatively uniform patterns, or like an early deviation pack shows us warmer area, which increases the risk or produces a stronger and the expanding hot region. So the safety response sequence is detected, verify, or classify. Okay. So and that time it just isolate it if necessary, or just record the event that time. Okay. So the digital twin here compares the measured behavior with the expected behavior. So the residual error is analyzed by the AI model, which can be generate a fault indication. So the major benefit here is lead time, or like earlier detection, which allows the controlled derating or cooling or service action instead of waiting for an emergency protection event. Okay. So another, if I would say the another major cause of this uneven battery behavior is the cell imbalance, which like smart balancing tries to reduce. And here you can see that the intelligent cell balancing, because cells are connected in series or parallels. We all know that. So the like cells connected in a like in series carry the same current, but they do not always have the same capacity. Right. So SOC resistance or temperature during charging, the highest voltage cell may reach its the limit first, and during discharge, the weaker cell may reach its lower limit first. So therefore, the unusable capacity of the complete pack is restricted by the weakest cell. Okay. So the passive balancing removes excess energy from the highest SOC cell through the resistors and the converters, because converters it just converts it into the heat, and it just simply and because it is just simple and low cost, but it wastes energy and it is generally slower. And the active balancing transfers energy from the stronger cell to weaker cell using the inductors and capacitors, or the DC-DC converter circuits. It is like more efficient and can improve unusable capacity, but it requires like more components and the complexity. Okay, so if I would say like an AI enabled balancing strategy can consider present cell voltage, cell SOC, internal resistance, temperature, all those things, instead of like balancing only when a fixed voltage difference appears. So it can predict what cell will become limiting during the next charge or drive. So this predictive approach can like start earlier, which reduces unnecessary balancing and avoid the creating avoid creating additional heat. Okay, so the goal is not to like force every cell to be numerically identical at all times. So the goal is to manage the pack so that so that no weak cell unnecessary limits safe operation. Okay, So the balance cell like also like if I would say like also help the pack accept fast charging or like more safely and consistently. And if I would say like this fast charging must balance four competing objective. First is the reduced charging time, then we have the limit temperature rise, then we have prevent lithium plating, then the preserve cycle life. Okay, so fast charging is like a multi-objective control problem. So the system wants to reduce the charging time and limits the temperature, the prevents the lithium plating and the and to prevent the or sorry or to preserve the cycle life. So improving one objective can like negatively affect another. So the BMS must continuously find a safe balance. Okay, so this here it is just showing you the like smart charging inputs. The stage one you can see here, the stage two, stage three, stage four, all these stages. So here you can see that SOCHO, SOH, cell temperature, internal resistance, cell balancing, all these are the inputs here. So the changing profile is just uh, divided into stages: the current, high current, moderate, control, sorry, current, reduced current, taper current, and the top of CV finish. Okay, so then it just gradually reducing a voltage, temperature, and aging risk here. So the if I would say like the continuously checked limits, I would say these three major limits are continuously checked, like voltage limit, temperature limit, and the aging risk limit. So the controller predicts near future response rather than reacting only to the present pole. For example, like even if temperature is currently safe, the model may predict that continuing the same current will access the limit after several minutes. Okay, so a closed loop process is select like initial profile or predicts the battery response or like apply the profile safety measures the actual behavior or update the model, optimize the next interval and at the end we will get the report or the results. Okay, so a key research message on this, basically this slide is nothing, just that the AI can like this AI can search and compare many candidates charging protocols more effectively than like exhausting physical testing, but this the final profile still requires proper the proper validation. Okay, so this is like a key message for all of you. Okay, so to implement all these intelligence, we need to decide which function belong inside the vehicle and which belong in the cloud. Okay, so as you can see at the here, the edge AI versus cloud AI. In the previous slide, we have seen that the 5 layers model. Okay, then there we have seen the edge layer, then the cloud layer, right? So this is the same thing. The edge layer lies. Okay, so basically this is a production smart BMS which just normally divides the intelligence between the vehicle and the cloud. So this is like not an either or the decision. So each location is suitable for the different task here. Edge or embedded BMS here, this edge or AM this embedded AI BMS which runs closer to the battery, it is just best for the uh, like uh, the safety critical local control or contactor control, current and power limiting, all these things. Okay, so the advantage are low latency or predictable response or the local data privacy. The limitation is restricted processor power or the memory and the energy. And if I would say the cloud platform, if I would say about this cloud AI, is the best for the fleet level analysis, like long time degradation modeling, or like you can see here the large model training, cross vehicle comparison, all those things, and the digital twin simulation. Okay, so it can use data from thousands of vehicles and much larger like computing resources. So however, it just depends on the commutation, communication, and should not be required for an immediate safety action. So this data flow diagram is just showing you that the service or the vehicle may upload the summarized data, health indicators, or charging history, or selected time data series. Okay. So the cloud may return updated model parameters, calibrated AI models, or maintenance recommendation, charging, and some thermal strategy. So the recommendation principle is just clear. Like safety decision must the safety decision like remain local, or while this the cloud support learning and the long term optimization works that there. Okay, so when many vehicles contribute this data over time, we create fleet learning and a continuous battery digital thread. Okay, so here it is showing you that the battery digital thread connects data across the complete life cycle, cell design, manufacturing, pack assembly, end of line testing, vehicle operation, charging. It is just showing you the digital thread here. The value of digital thread is continuity, right? Like a field problem can be traced backward to the manufacturing data, and a manufacturing change can be evaluated through long-term field performance. Instead of keeping information is like in isolated departments, the digital thread just creates a connected history from the battery. Okay, so the fleet learning uses data from many batteries to compare behavior across climates and this usage patterns, or identify the recurring manufacturing or the supplier issues. Okay, for example, like if one group of vehicles shows higher resistance growth in a particular climate, and the company can compare cell batch cooling performance, charging pattern, and some software versions. So the conclusion from one vehicle becomes more reliable when supported by another patterns across a fleet. So this is just showing you that the standards for this digital twin life cycle management, the practical lessons for if I would say the beginning of the battery life to its final reuse or the recycling stage here, because this connected intelligence affects the safety critical equipment, functional safety, and cyber security as or are because cyber security is also essential here. Okay, so this is showing you that the AI models may recommend an actions, but it must operate inside validated safety, or safety or security and the battery compliance boundaries. So this slide just showing you that here there are three overlapping areas. You can see here the AI smart BMS, then the security and the safety or battery compliances. Okay, so functional safety addresses just hazard caused by the malfunctioning electrical or the electronic system. Okay, then cybersecurity protects the vehicle against this unauthorized access and the data manipulation and the malicious software. Okay, then the battery safety. Oh, is it just nothing but just regulation which is defined, required, or test and the operating expectation from the electric vehicle batteries. And then the smart AI enabled smart BMS. This is just safeguards includes secure boot, signed firmware, or like some AI models, Okay, and there are encrypted like encrypted communication as well in this. So we just by like these controls, that because these controls are like important, because an like incorrect model update or like corrupted message could affect charge limits. Okay, then like power limits or the thermal control are also in this. So is safe, the main thing is like the safe design, because it just therefore separates the recommendation for the permission. Okay, so AI may recommend increasing charging current, but a validated safety layer checks voltage, temperature, current, and approved operating limits before affecting or allowing the action. So if the AI becomes unavailable or gives an implausible output, the system must return to known safe mode. Okay, so the trustworthy smart BMS development requires accuracy, explainability, some these what we can say like the cyber security validation, and some for like fail-safe behaviors. Okay, so to build real these reliable models, we also need uh, suitable data sets and like some these disciplined development workflow. Okay, so this is here you can see that the because the battery AI development begins with the representative data, right? So department is also you can see here the departments of energy, battery data, drive cycles data. All these things are here. So these are, and here is the 10-step model development workflow is also shown here, that the like then we collect this data and clean and synchronize it, and like it is useful feature because to train the models and to validate it. So it just test it on an independent data set, prevent data leakage, follow like best practices, and monitor the deployed model. So here this the three data group is also shown here, that the training set is just used to learn model parameters. Okay, and the validation set is used to turn the model and like compare the alternatives. Okay, and then I would say the independent test, this is used only for the final unbiased evaluation. And the data leakage happens when this the information from the future or from the test set accidentally influences the training or the creating unrealistic good results. And deployment is not the end basically. So the model must be monitored in real vehicles for changing data distribution, sensor drift, new battery versions, and some unusual conditions. Okay, so a model that performs like well in the laboratory may not perform equally well across climates, drives, and the aging states. So a reliable AI is created by a reliable process, not only like by a not only by like a powerful algorithm. So then this next slide you can see here, it just gives us the research examples with showing what these methods can achieve under the control conditions. Okay, so these are some case studies with some real results. Okay, then you can see here the 124 cells early cycle life prediction, where we can they have tested with the 124 cell. The case study second was on the fast charging optimization, then the real time SOS digital twin, and here is the less than 1% of benchmark error. Okay, so the purpose is not to claim that one result will appear to every battery. So So the purpose is like to show the types of benefits that have been demonstrated under this specific experimental condition. As you can see here, the 124 cells, LFP cells are used here for early cycle life prediction. And the approach here, this the approach uses information from early charging behavior to estimate the future lifetime. Okay, so this slide basically just reports approximately 9.1% of test error using the initial 100. Like this is early cycle data. So the learning point is that future degradation can sometimes be predicted before a long full time or the full life test is completed. Okay, then the second, you will see here the two focus on the fast charging optimization. So like a large number of candidates, 10 minutes of charging protocol were evaluated, and an AI supported search identified like high cycle life option is in 16 days. Okay, so it just instead of like an estimating exhaustive testing time of more than 500 days, the benefit is faster experimentally search, like not removal for of safety validation. And then the third, we can see here the real time SOH digital twin. So here the case study is just showing us that it continuously construct battery behavior and reports benchmark error uh, or like below 1% under the stated study conditions. Okay, so basically it is just nothing but it just telling us that how the case studies are helped us. Okay, then if I would say the implementation roadmap for a smart digital twin. Okay, so these there are the key performance indicators are shown here, the operation key performance indicators are shown here, then the where we have the future deployment, then the final conclusion. So a smart BMS project must be measured with these technical and operational performance indicators. Okay, these technical includes all these things, then the operation include all these things. So if I would say about the operational, so a model can be accurate in a report but still fall as a product if it requires too much like computation, and it produces too many false alarms or like doesn't improve the fleet operation. Okay, so and if I would say about the future deployment, basically it is just physics informed neural networks or the like self learning battery models or feed rated fleet learning and like battery foundation models, all these things which which makes this AI explainable or if I was like a grid connected optimization. Okay, so the evolution, if you'll see here that this bottom moves like from reactive BMS to predictive BMS, then the autonomous battery intelligence. Okay, so the future system will not only protect the battery based on current condition, it will predict what is likely to happen and optimize the operation safety within the verified limits. Okay, so now let's convert these performance goals into the practical implementation. Okay, so a smart BMS like a digital twin should be introduced in studies. As you can see here, the roadmap begins with the phase one, define use or case. Okay, such an SOC improvement, SOH monitoring, fault, all these things. Then the phase two, we have established data foundation, or some build data dictionary, synchronized BMS, all these things. So it just validate it across the temperature and current ranges and measures the performance of the conventional estimator. Okay, then the if I would say about the phase 4, here it is like AI enhancement such as residual correction or like anomaly detection, which compares it with the battery, sorry, with the baseline. Then the quantify uncertainty is shown here. So then if you will say here the phase 5 is the hardware in the loop validation. This is exactly the same thing we have studied in the CAN system. Like there is a hardware in the loop, like like or the suppose if you have studied about the V model, the MATLAB, there we use a hardware in the loop because when you do the simulation in your software or whatever the things you are implementing in your vehicle, so at the end you need a module or the anything, the Arduino or the anything you want to do, like make a changes in your vehicle. So you just make a V model or a model or the simulation model in the softwares. Then you will implement, then you will like you implement all these things in the hardware, right? And the current or the real time things you are watching in your monitors. So to do the connections and after checking it on the real time monitoring in your vehicle, because we can't do the testing with the physical vehicle, so it will cost us much higher, right? So first we do the simulation or the software things, then we will implement all these things in the hardware. Then there you use a Arduino or anything. Okay, so this is basically the hardware in the loop validation. There you will check the SOC or the temperature condition, which confirms like safe fallback or the major processor time and the memory, this memory use. Okay, then at the end we have the phase 6, pilot fleet deployment. So it just start in the shadow mode, like where AI observes and predicts. This predicts but doesn't control or like compare its result with the service and the laboratory findings. Okay, so then it just gradually enables the this approved function, and here the each phase has a review, safety check, and the validation gate. So this destination is validated fleet deployment, not like this laboratory demonstration only. Okay. Okay, so here I have one question, like why should an AI model be deployed in observation mode, like before it is allowed to control the charging or the cooling? Just give me a second. Hello, Raju sir, are you there? Or Abhishek? Hello,
Yes,
hello,
Akash.
Raju. Yes, sir. Sir, have you pasted the form link here?
No, just a second. I'm fading.
And where is Abhishek?
भाई बात मेट्रो के लिए किधर से जाएंगे? इधर से या इधर से? इधर से भी जाता हूँ कहाँ? क्यों रखता है? इधर से भी जा सकता है।
Please mute yourself if you are not asking any questions. Okay. Uh, how many of you are in here? Please just fill the Google form, okay, or the feedback form here. Uh, Abhishek, are you there? Sir, have you told Abhishek to about Hello, Raju sir.
Yeah, Akash, actually, I'm just outside right now. Can check like if I'm safe is there or not. It's fast to join or you can just or give me a moment.
Hello. Sir. Sir, have you pasted the link?
Yeah, I've shared the link. You can check it.
Please fill the Google form, or if anyone have any questions or doubt till now, just you can unmute yourself one by one. Okay. You don't have the link? Just give me a second. I am sharing you the link. Okay. Anyone have any questions or doubt? Please, you can unmute yourself or just tell me the query if you have any query.
Uh, yeah, I have one question. So this actually this digital twin require a lot of data, right? I mean, so where do you get this
Can
data?
you just speak little bit louder? Actually, your voice is not clearly. I can understand. Yeah.
Yeah, yeah, this is Venkat. So I wanted to understand like the data set you taken from like already existing data set, or you done some experiments on the battery.
Sorry.
So the data sets you used for the AI or the model training. So
Yes.
you collected from the lab experiments or any existing public data sets.
So you are asking about the case studies I have mentioned here.
Yeah.
Actually, these case study I got on the internet, and when I was preparing this PPT, I want to show you about the some case studies. Actually, this technology right now in India is not that much popular, or most of the vehicles, or like our company is also working on this technology to implement in our workbenches, because right now we are like heading towards AI. So we want to introduce our workbenches with the digital twin technology. There you can easily understand or visualize the 3D map of the vehicle, or the if you are testing the motor, or suppose you are testing the controller, or suppose you are testing the battery. Okay, so these digital twin will help you to find out the error in your vehicle. And if you are saying about the case studies, these case studies I got on the internet. There the some maybe engineers or some tech
Yeah,
have performed
My,
this
my question
digital
is
twin in
different.
their
My
system.
question is different. So I'm asking about suppose if I wanted to train the AI model for a specific predictions or anomaly or any other things, I need a collection of data, right? I mean, so I have
Yes,
to do
yes,
some
you
kind of
need a collection.
yeah. So how do you get this data? Do you have any verified data with you, or like are you done any experiments in the laboratory? How do you say these concepts are valid as per the technology?
So the main things, or I would say that here the BMS, or then the motor controller, or the temperature sensor, current voltage sensors, GPS, IMU, CAN bus. That in the slides I have mentioned the 5-layer model, and there I have shown you the edge controller, which is used. Edge controller means the Raspberry Pi or the Jetson is used there. Then we use some networks, 4G, 5G, Wi-Fi, and then the above layer we have the cloud platform. Okay, then there the cloud in the cloud platform, the data is getting stored with the help of sensors. Okay, and this digital twin, after this the cloud platform, the digital twin model will appear in your screen, or you can easily see. So AI, or if I would say the analytics about the battery, then you can easily see on your dashboard or mobile. So the main components are required. If I would say about the hardware components, is the BMS, voltage current sensors, or the motor speed, RPM sensor, GPS module, or some like modules like Raspberry Pi, NVIDIA Jetson, any edge computer, or one CAN interface or the CAN transceiver is also required there. It is about the components or in the hardware. Or if I would talk about the software thing, there we need a requirement of Python or C++ or MQTT for the communication, and some database like the InfluxDB, or many systems like I am not like coming to mind right now. This is not coming to my mind, like Postgres, SQL, something like that. So after this, the software, we have the dashboard. Then there the dashboard, we use the Grafana, Power BI, some custom web app. Okay. Or some AI libraries as well, like PyTorch, if you have heard about this, or the Scikit-learn. So all these data which is getting we are from the hardware or the software things, this data is to collect, and the digital twin should like continuously here is receiving data such as like battery from the battery. We know that the SOH, all those things are we are getting, okay, from the charger environment. Okay. So this virtual model like can monitor with the help of these softwares or the hardware thing. We can easily make a virtual model. There we can see the monitor, or there we can monitor the battery health in real time, or predict the battery degradation, or like do some remaining useful life. Okay. And if I would say like the AI application, which is for example, machine learning models includes in this like battery life prediction, which uses the historical charge I just mentioned you in the fewer slides back, and some anomaly detection to identify the unusual temperature or the current patterns. Okay, and some range prediction as well. Okay, so the data flow, how the data flows like from the battery sensors, then the BMS, CAN bus, then we have the Raspberry Pi, then we have the MQTT over the like Wi-Fi or the 4G, then we have the cloud server, then after the cloud server we use the digital twin model to check the battery health prediction, all these things. Okay. And
Suppose,
suppose like, yeah, like
let's say,
suppose you are making a, yeah.
if I have vehicles, I have a battery in that and also the BMS in that. And I don't have any
Yes.
kind of, let's say, AI models in the BMS. It is a conventional BMS. Now I'm
Okay.
collecting the data through some kind of MQTT or some kind of protocols to the
Yes.
cloud or to the edge device. The edge device can
Yes.
be within the vehicle or it can be very near to the battery. So let's say, as you mentioned, the edge device, the embedded processor, which will take care of the safety critical actions.
Yes. Exactly. Yeah.
So now I can segregate the cloud with the edge, right? So now let's talk about the edge. So my question basically about the data centered collection. It's about like let's say if I wanted to predict the SOC, I need a measured voltage and current. So I need a
Yeah.
physical battery. Right now I don't have those batteries. I want to use some kind of public existing experimented data from any of these sources. Do you aware of those sources where we get this experimented data?
Yeah, like if you want the existing data, maybe I will provide you, or you can just search on the internet. You will get the existing data of these digital twin. So, like, if you will search about this technology in your browser, then you will find the how you can do the edge, or like from the edge how you can store the data in the cloud system.
Okay.
Okay. Yeah.
Okay, I will contact you later. Thank you.
Yes, thank you so much. Anyone else? Sir, have you pasted the link? Rajiv sir, have you pasted the link there? The feedback form link. Please, everyone, please fill this feedback form, and after this you will get the certificate. Or Abhishek, have you joined the session?
Yes, sir.
Yes, Abhishek, please continue.
Hi, good evening, everyone. This side Abhishek. I am here to introduce you guys with uh, with a master's certification in EV technology approved by AICTE. I would like to tell you a little about it. So, in the course you will be getting live classes with projects at ISIE India EV Labs and industry relevant curriculum designed and taught by industry
Abhishek, can
experts
you hold on?
and hands-on projects. Yes, sir.
Yes. So everyone, so thank you for participating. So the Abhishek was introducing regarding one of our course. Like as you know, like ISA India is working in different segment, and one of segment is like a skill development where we run different type of courses. And one of courses which we run, which we are running association with AICT. That is a 6 month master degree program where, like as you have seen, like the Takas has shared the session, the knowledge they have shared within 1.5 hour. So it was just a webinar session that is like for 1.5 hour. But that course is complete EV technology course starting from basic to detail. What are the things which is currently going in the industry? Starting it's related to the battery, motor, controller, wire harness diagram, and everything. It's related to everything. And apart from that, as most of the college have already started their academic season, so students who, if anyone wanted to opt a internship program, that is related to again EV, and it's available in both mode, online and hybrid mode. So that is like if any students wanted to submit their internship certificate and they want to, like most of the time what happens like now like the students are serious and they are actually going to the company and the industry getting trained and getting the certificate. But earlier, like most of the students used to arrange their certificate and usually they submit those certificate in the colleges. So like we do provide a valid internship program which is applicable in the colleges and interview and anywhere. So if you want to submit, if you're going to submit any certificate or those certificate to any interview and even like as a internship program in your college, so that will be also applicable. So the Abhishek was telling about that only. So suppose if anyone is having interest related to this any program, so Abhishek will ping their number in the chat box and they will share the details regarding to that in the chat box also in only. So if anyone is interested, you can you can contact Abhishek, and there is a scanner is already given on the you can see like in the screen. You can call Abhishek and Pratham, so they can help you with that, and you can even scan that QR code for more details. So anyone is having any query? So yeah, if suppose if a scanner is not working, you can directly contact Abhishek Pandey and Pratham Bajpayee. So they will help you with that. Okay. If, and I'll request you like like in every week, sir used to make this effort to introduce about new technology and new things regarding the what's going on in the industry. So it will be great help for us and for sir. If you will fill the if you will guys fill the like review form and so whatever you will fill it and what are the area where sir and we ISI India can improve and what are the other topics you wanted to learn in the upcoming season. So accordingly, we can improvise and the sir can improvise and we can give a we can deliver a better session. Okay, and I'll do one thing. I think just a second. Let me check with sir. Okay, no issue. I think. Okay, so see, the thing is, I think many students have already made the meeting. So I'll request you. So please do fill the Google form, the review form. So I'll capture the attendance from there only for the certificate. Okay. So make sure like everyone filling that review form. So I will capture the attendance from that Google form only, and certificate will be designed and prepared and sent according to that only. Okay. So thank you everyone. And if anyone is having any doubt, you can ask. I'll answer that. So Shiv Prasad, you can reach out to the given number, that is Abhishek Pandey and Pratham. Anyone you can call, he will guide you with that. Okay. Anyone else is like anyone any doubt? Otherwise, we'll end the meeting. Okay. So thank you everyone. Thank you for joining. Have a great day. We'll meet in the next session. Okay. Thank you. Thank you.